We're now at lecture 13, talking about functions of a square matrix. We've looked at this a little bit when we looked at computing a to the power k. Now we're going to look at it in more general detail. So there are several methods for computing functions of a square matrix. There's the transform method, there's the spectral mapping theorem, and there's the Cayley-Hamilton theorem. These are three methods for computing functions of a square matrix. So, solution by transform. We'll look at that one first. We wish to compute a function of the matrix A. For example, in discrete time, we have the state transition matrix A to the power k. In continuous time, we have the function e to the at. And so, in discrete time, we can compute a to the power k as z inverse, the inverse z transform of the quantity zi minus a quantity inverse. Or we have the inverse Laplace transform of si minus a quantity inverse, which is e to the at. In either case, these require a symbolic matrix inverse. So S is being a symbol, A is a numerical matrix, and so we have a symbolic matrix inverse that we need to compute in both of these cases. So let's look at an example real quick. This matrix is not diagonalizable. It's a defective matrix. So when you compute Si minus A inverse, you get 1 over S plus 2 and then powers of 1 over S plus 2 in this matrix. So if we use the inverse Laplace transform, these are inverse Laplace transform for various functions, various powers of S plus 2 in the denominator. Notice that each power gives another power of t out front. So t e to the minus 2, e to the minus 2t appears in all of these, but I can get a t e to the minus 2t, t squared e to the minus 2t. Okay, so for various powers of t, we get that. Similarly, e to the at then is we take the inverse Laplace transform of each term in the matrix Si minus A inverse, and this is what we get. So this is the matrix exponential, and how to do it using the transform method. So this is an example for continuous time. We could similarly do an example in discrete time. The spectral mapping theorem. Given a Jordan decomposition, so A is equal to V capital lambda V inverse, we can compute an analytic function f of the matrix A using this method. F of A is equal to V f of lambda V inverse, where the function f of lambda is sometimes easier to compute than f of A. This works really well for diagonal matrix, not so well with defective matrices. If we have a diagonal matrix, if lambda is a diagonal matrix, even if we have repeated values along the diagonal, as long as it's diagonal and not defective, not requiring a Jordan form, then f of lambda is just f of the diagonal elements. F of capital lambda is the function of the little lambdas. And so it's a very straightforward thing. So if we're looking for e to the lambda t, for example, like e to the at, we would compute, we would have e to the lambda 1t all the way down to e to the lambda nt. Or if we were looking for lambda to the power k, we would just have the individual lambdas to the power k. And so that would be f of capital lambda. To find f of a, then, we would just compute it from the eigenvector matrices this way. So it's very straightforward that way.